So for decades, power electronics was this quiet, almost invisible engineering niche.
Right. It was always important, of course, foundational to everything,
Hmm.
but it was only really discussed by people who, knew what a gate driver was.
And as our sources put it, genuinely enjoyed pain.
Exactly. But what's so fascinating is how that shifted. I mean, it has scaled up so fast that it's not just an engineering challenge anymore.
It's become what our sources are calling a civilization scale bottleneck.
It really has.
Okay, let's unpack that right away. How did the control of electricity suddenly become this massive bottleneck?
Well, look at where we're putting all our energy and investment.
Hmm.
Everything is becoming electrically hungry, mobile, automated.
We're talking EV drivetrains, massive solar and wind farms, AI data centers.
High-speed rail, robotics, aircraft electrification, you name it. We
Yeah.
are trying to push just unprecedented amounts of controlled power through systems that are running headlong into these fundamental,
These physical limits.
exactly, physical limits.
Yeah.
And when you look across all those different fields, they're all fighting the exact same curse.
And that's our mission for this deep dive, to really get into the nature of that limit, look at the consequences of the current workarounds, and then talk about a new component designed to tackle it at the root.
And our sources are incredibly clear on what that curse is. It's one word: heat.
Heat.
Heat is the non-negotiable tax you pay for every single conversion, every switch, every control loop in a modern power system.
And as we demand more and more power density, thousands of watts cram into smaller, lighter packages, that heat tax starts to feel less like a small fee and more like this crippling tariff on any kind of innovation.
Precisely. The more you ask a system to do, the faster and tighter you control it. The switching losses just accelerate, and that energy has nowhere to go but out as heat.
So let's dive into that. Section 1, this constraint that engineers have nicknamed the heat wall. Why is heat the core constraint? Why not just call it a side effect of, inefficiency?
Because it ends up dictating the entire design of the system. When you're forced to deliver that much power in a small space, the presence of heat forces these sweeping compromises. They go way beyond just wasting a bit of electricity.
So you're not just designing a power system anymore. You're designing a system to survive its own thermal output.
Exactly. You're forced into heavier thermal management. We're talking bigger heat sinks, complex cooling infrastructure like fans, ducts, pumps, liquid loops,
All of which adds cost and weight and points of failure.
and maintenance.
Mhm.
And in power electronics, volume is often reliability. The smaller you try to make it, the closer you get to that thermal limit, and the whole thing just becomes more fragile.
That brings up a critical term I saw in the sources: derating. Can you walk us through what that actually means for a system's real-world performance?
Deberating is basically the engineering term for when reality hits the sales brochure. It's the system admitting that under real-world conditions, a hot day, a dirty filter, a continuous high load, it can't safely deliver the power it was rated for.
So if I buy a 100 kilowatt fast charger, it might only be able to consistently give me, say, 70 kilowatts if things get too hot.
That's often exactly what happens. The system's own firmware is constantly monitoring the temperature. And to prevent just catastrophic failure, it pulls back performance. You pay for 100, but you only get 70 when you really need it.
And that really highlights the core insight here, doesn't it? The reliability ceiling is tied directly to the thermal margin.
Absolutely. The moment that thermal margin collapses, reliability is the next thing to go. It's why power engineers don't really sound like efficiency experts. They sound more like structural engineers.
What do you mean by that?
They aren't worried about whether the circuit works today. They're worried about whether it will still work after, and this is a direct quote, 10,000 ugly cycles. They design for stress, and heat is the ultimate stressor.
That analogy really grounds it. It's about longevity under punishment. And there's probably no place where that punishment is more visible right now than in data centers.
Oh, absolutely. They are the canary in the high-power coal mine.
It seems like modern compute, especially for AI, is shifting from being just a chip problem to being fundamentally a power delivery and heat removal problem.
That's the heart of it. We all focus on the next great piece of silicon, but if you can't get clean, efficient, predictable power to that silicon at scale, and then get the heat away from it, those racks just turn into, as one source put it, very expensive space heaters.
So a multi-billion-dollar investment in compute can be completely kneecapped by the power handling system.
Completely. And data centers are fighting this on multiple fronts. First, just getting the power to the building. Securing 50 or 100 megawatts from a local utility is a massive infrastructure battle.
And once that power is in the building, the fight moves inside and the heat starts to multiply.
Right. Every time you convert the voltage down, from the facility level to the rack level to the chip level, you pay that heat tax. And with thousands of servers, each with multiple conversion stages, a tiny inefficiency creates what you could call a tower of thermal debt.
And that debt just keeps accumulating.
It accumulates, turning a minor issue at the component level into a major infrastructure challenge for the whole building.
So what are they doing now to survive this? What does the cooling look like?
Heroic efforts. I mean, we're seeing the rise of things like immersion cooling, where entire servers are dunked in specialized fluid, or complex cold plates where liquid is pumped directly over the chips.
Which sounds incredibly expensive and complex.
It is. It's expensive, it's heavy, it adds a whole new system of pumps and heat exchangers, each with its own failure modes. And that's why reliability is so critical. Any downtime from thermal stress is just not an option for this kind of infrastructure.
So power electronics isn't a utility anymore. It's the mission-critical foundation for the entire cloud and AI revolution. And heat is the thing that quietly inflates every single one of their constraints.
Exactly.
Okay, so the problem is huge. It's systemic. The industry obviously hasn't been sitting still. They have developed some incredibly clever workarounds.
Oh, they deserve a ton of credit. The industry has fought back hard. We've seen better semiconductors like silicon carbide and gallium nitride that switch a bit cleaner, smarter packaging. And, yes, our sources use the phrase heroic firmware hacks.
Heroic firmware hacks. I love that.
Right. Complex digital controls trying to squeeze every last drop of performance out of a component right at its thermal edge.
But the core frustration seems to be the pattern here. It feels like all these fixes are about managing a symptom, not curing the disease.
That's the key takeaway. Most of these brilliant solutions are designed to manage heat after it has already been created. They dissipate it, move it, or spread it around. The underlying architectural problem is still there.
And that architectural problem is described as mismatch, using electronic switching to do a job that is, quote, magnetic by nature.
That's where we get into the physics of it. A lot of power control, transforming voltage, filtering current. It inherently involves manipulating magnetic fields with inductors and transformers.
But the main tool we use to control that magnetic process is a solid-state electronic switch.
Correct. We're using a semiconductor switch, which is amazing for high-speed logic, to do this high-energy job that's governed by magnetic principles. And that friction, that mismatch, is where a huge amount of inefficiency and heat comes from.
Because the switch is essentially fighting against the magnetic parts of the system every time it turns on and off.
Exactly. It generates massive losses and a ton of electrical noise, or EMI, precisely because of that fight. It forces designers to add huge amounts of filtering and shielding. One engineer described it as having to build a lead box inside a lead box.
And meanwhile, the thermal management system just grows and grows into this huge parallel subsystem.
It really does. It has its own bill of materials, its own power draw for the fans and pumps, and its own failure modes. And on top of that, designers have to plan for the worst-case scenario, a fault, a load spike, so they're forced into costly oversizing.
So we're building these smarter machines that spend a huge amount of their own effort and cost just surviving the harsh conditions they create for themselves.
It's a cycle of self-inflicted wounds.
Which brings us to a potential solution. Our sources point to a foundational fix, a different approach.
Right. They suggest the focus needs to shift away from managing the output and to changing the actual mechanism of switching. This is where a company called FluxWorx comes in. They're developing what they call a magnetic transistor.
And the sources are very clear. This is not just a slightly better semiconductor.
No, it's an architectural change. The core idea is to reduce the penalties you get when you force standard silicon to do all the heavy lifting. It shifts the burden of switching to a component that's designed from the ground up to handle the magnetic nature of the task.
Okay, let's ground that for a second. How does shifting that burden actually reduce the heat tax?
Well, think about a standard switch. When it turns on and off really fast under a heavy load, that tiny moment of transition is where there's immense stress and heat. It's going from fully off to fully on against all that stored magnetic energy.
That's the friction point.
That's the friction. The magnetic transistor integrates magnetic principles right into the switching component itself. It allows the system to manage those transitions much more gracefully. It offloads the really stressful, high-speed work from the silicon, which means far less energy is wasted as heat during that critical moment.
So instead of creating a ton of friction and then building a huge system to get rid of the resulting heat, You're just reducing the friction in the first place.
Exactly. You're avoiding the creation of the heat tax rather than just getting better at managing it with fans and cold plates.
That sounds
Yeah.
revolutionary, honestly. Moving from just incremental gains to a foundational fix. What are the barriers for something like this?
Adoption is always the big one. Power engineers are rightly conservative because a failure can be catastrophic. You don't want to risk a 50-megawatt data center on unproven tech.
But at the same time, the pain is so acute right now.
The pain is so acute that the incentive to find a breakthrough is massive. So this component is really positioned for those systems where today's solutions are just completely dominated by thermal limits and all the engineering overhead that comes with them. The goal is to make heat, less of a dictator in the design process.
Less of a dictator. I like that. So if that's the goal, let's move past just the efficiency number. What does less heat actually buy you, the engineer or the user?
It buys you design freedom. It buys you capability. The efficiency number is just the ticket to get in the door. The real value is in all the cascading advantages that it unlocks downstream.
Okay, let's run through that list because it shows how one change can simplify an entire system.
First, your systems can be substantially smaller and lighter. You've drastically reduced or even eliminated the need for those massive heat sinks and all the cooling hardware.
Which gives you higher power density. More watts in a smaller box.
Critical for EVs, for aerospace, for robotics, and with fewer moving parts, fewer fans, fewer pumps, you get a massive leap in reliability, less complexity, less maintenance, less downtime.
Which, for data centers, is everything.
Yeah, the priceless.
And let's go back to demorating. What does this mean for that problem?
It means the system actually delivers on its promise. That 100 kilowatt system doesn't drop to 70 on a hot day. It might consistently deliver 95. That extra 25 kilowatts is pure usable capacity that you already paid for. It massively improves the return on investment.
So you get the performance you were sold without needing that heroic thermal engineering just to keep it from melting.
And the control system gets simpler too. The whole system isn't constantly stressed at its thermal limit, so the protection and fault handling can be less complex. The total cost of the system drops, not just because of the parts, but because the engineering effort to make it survive is so much lower.
So the key insight here is really profound. In these high-power systems, cooler isn't just about comfort or saving a little on the electric bill. Cooler is capability. It fundamentally resets the boundary of what's even possible to design.
It creates a new ceiling. When you raise that thermal ceiling, you unlock design space that engineers simply couldn't touch before.
Okay, wrapping this up, let's synthesize the big picture. We started this by framing power electronics as a civilization-scale bottleneck. What does this deep dive really tell us about the future?
It reframes the whole challenge, I think. We spend so much time and capital on power generation and storage, the solar panels, the batteries. But the primary constraint we're facing now isn't a generation crisis. It's a power handling crisis.
Right. We've spent decades perfecting the engine and the battery, but the transmission, the conversion layer, is the piece that's constantly shaking itself apart under the strain.
That conversion layer is where the heat builds up, where the complexity multiplies, and where all the hidden costs creep in. Technologies that aim to fix the problem at the fundamental physics level, like this magnetic transistor, they're not just nice to have. They're essential to keep the whole machine from shaking itself apart.
It's about making sure the foundation can actually handle the incredible demands we're about to place on it.
Absolutely. And here's a final thought for you to mull over. Since power electronics is now so deeply embedded in everything, how any groundbreaking advances in robotics, in EVs, in the next generation of AI are waiting not for a faster chip or a bigger battery, but for a fundamental fix in the way we simply convert and control the power flowing through the system.
Wow.
It means the ceiling on our ingenuity, in many ways, is literally set by a thermal budget.
That's a powerful thought to end on. The future isn't just about running faster, it's about running cooler. Thank you for walking us through this.
My pleasure.